Okay, so what we're going to do here today is we're going to jump into this topic known as first order differential equations. And we'll say ODEs because again, we're talking about ordinary differential equations as opposed to partial differential equations. And when I'm looking at first order ODEs, these differential equations, there's different classifications that I want to be aware of when I go about the problems because based upon the structure of the equation, I'm either going to do one thing or another. First order differential equations, and in particular what I'm talking about is first order linear differential equations, they're going to have this type of structure where you're going to have some kind of function. I'll just call it P here for the moment. We're going to have a y prime. We're going to have a q of x. We'll say y. And then maybe something over here, maybe call it an r function, maybe call it r. Lots of times when we're going through our problems, we want to make sure we have a nice canonical form. We want to make sure we have a nice structure to that. And that's something you need to be observant as you go about your problems, because if the equation you're working with doesn't really fit the formula, the process, guys, it's going to throw it pretty much every single time. So you got to make sure you're very observant of that. And I'll point that out on different equations as we go through this whole entire process here, looking at these different types of systems. The one that I want to look at here today is probably by far the easiest one that you're ever going to experience. So I guess you can say it's all downhill from here. And the first type of differential equation is known as a separable differential equation. These equations have a particular structure. And again, we're still talking about just simply ODEs, but I'm going to say DE now for differential equations. And these types of differential equations, we're looking at y prime equals a function solely in terms of x, and then another function solely in terms of y. So if I can take a differential equation and factor it, if I can do this, then I got this particular structure. And if I have this particular structure, then I can possibly solve. I say possibly because sometimes you're not going to be able to solve your differential equations. And in those situations, we can resort back to looking at things from a geometric perspective. Look at those isonclines, looking at the slope fields, kind of get a better understanding, a bird's eye understanding as to what's happening with the solution set. But here, what I want to do is perhaps take y prime, and we can use notation of dy dx. And there are lots of different notations I could use for a derivative. Again, you could say a differential operator, capital D, on the function y. We'll get to this eventually, but for right now, this makes a lot more sense. And just remember where this came from. This came from the very beginning of calculus when you're looking at some kind of curve and you're asking yourself the simple question, if I was to take the secant line, maybe swing it down, get that point of tangency, I would talk about the average rate of change. So I would measure the x, measure the y, see how that's changing. And if I'm infinitesimally small, if I'm small enough, if I'm close enough, eventually this starts behaving like the derivative. This over here, this is a fraction. This over here, that's not really a fraction. But we pretend like it's a fraction when I'm talking about y prime. With all that said, we're going to pretend like it's a fraction anyways and sweep it on the rug and don't worry about it because it's going to work. It's going to have the right mechanics where things are just going to click together. What you would do to separate is all the y's to one side and all the x's to the other side. Take the dx, bring that thing up. And then take the g function, drop it down below. We have successfully separated out the x's and the y's in a differential equation. Now, after you do this step, the next thing is to come through here and you integrate. Why would you want to integrate? What happens when you integrate a derivative, this dy? You're going to get back to the function of y. And that's what we're after. We're after the function y. or maybe something implicitly in terms of y. If I want to solve this, there is one way of how I can approach this problem. I can simply just go ahead and maybe integrate across and see what's going to turn from it. But before I really start diving into it, can you see what the answer is going to be before you do it? It's a function whose derivative is proportional to itself. What kind of functions have that characteristic? Exponentials. So I should see in the very end something like e to the power of 2x. If I have e to the power of 2x and I take its derivative by the chain rule, and I see that, that's my function y. So let's actually stress test this like we do in computer science. We know what the answer is. Let's see if the hardware can actually go through the calculations, can actually perform the task. Get y prime by itself, take the y prime, recalibrate it, dy dx. X is to one side, y is to the other side. Move things around. You could leave the 2 right there, or you could bring it along for the ride. It's really your choice. I'm going to leave it over here on the right-hand side. Just leave it alone. The next thing is, after I have this thing completely factored in terms of x's and y's, functions of x's and y's, take the dy dx, pull it apart, is to integrate. If you want to, guys, you could say step 1, step 2, step 3 in your notes there. So you remember the process which you're going to need to do to go through this. If I integrate the right-hand side, we're going to get 2x plus c. There you go. Don't forget the plus c. If I integrate the left-hand side, what am I going to get? Natural log. Now, technically, it's really the absolute value. But we're going to kind of sweep that under the rug because we're really just looking for a mechanism, a mechanic that's going to work. Solve for y. To solve for y, exponentiate both sides. And what happens when you exponentiate the left-hand side? Argument comes dropping out. You use properties of exponents now to take this and clean it up. E to the 2x, e to the c. And here's where you got to be a little bit careful now as you get deeper into differential equations, as you chase that rabbit trail that we're going to be chasing here for the next few weeks. Yeah, c is an arbitrary integration constant, but it is an arbitrary particular integration constant. I got to be careful. I don't really want to say c here when I have e to the c. It is a constant still, and it's kind of based upon what's happening here with c. In this particular case, once I have c, I just want to kind of lock it down, and I really don't want to touch it again. Back here, when I'm integrating, I can say c1, c2, combine them all together and just call it all c. But once I call it c, I just want to kind of float it around and not use that magical property of integration, because that could cause riptides within your problem, especially when you start looking for particular solutions. What I'm going to do is just call it a. So y equals a e to the 2x. And there's my solution. And that echoes exactly what we thought was going to be at the very beginning. At the very beginning, I said the solution is going to be e to the power 2x. It is, but that was a particular solution. If I give you some more information, such as suppose that y of 0 equals 1, where I have initial condition, we'll call it IC here, just something that's been initialized, the condition. I'm telling you a particular solution. I'm really locking this down. So in this particular case, I could take the x, set equal to 0, e to the 0, a, and then 1. That's 1. 1 times a is a. A is 1, thereby giving us y equals e to the 2x. So more than likely, what's going to happen a lot of times in your differential equations, you're going to have some kind of constant floating around, and you're not going to be able to figure it out unless you're given some extra information. Okay. Now, that's not always the case, but it could be the case. And you'll see that too as we dig deeper and deeper into this topic. Before I move on to the next one, questions? Well, the first thing to notice when you're looking at a differential equation is what kind of structure does it have? And since we're talking about separable differential equations, it's probably going to be a separable differential equation. I got to be able to take it and factor it again. If I can do this, we got it. In this case, though, it's not x, it's t. It doesn't really matter if you call it t or x. This might be something in physics where t maybe corresponds to time. That might be where this came from. But anyways, I got to think about how I'm going to take y prime and turn it into some function in terms of t and some function solely in terms of y. What I'm going to have to do here is a little bit of algebra to get into the format that I need. So take maybe this part, throw it to the other side, because I don't need that on the left, do I? I just need a y prime, not y prime plus something. So over here, we're going to have minus y squared cosine 2t. On the left, y prime, recalibrate it. dy dx. This suggestive notation that we're looking at a fraction. Okay. X is to one side, y is to the other side. Let's see what happens. So take the dx, throw it over here, and you can keep the negative on the right. Keep it, it doesn't matter, just keep it up there somewhere. So we have, oops, I said x. See, made the same mistake, call it t. Cosine 2t dt. And over here, we're going to have dy and y squared. Everything over here is y. Everything over here is t's. Come through here now and integrate the left, integrate the right. If you integrate the right-hand side, we're going to get sine 2t divided by 2. Don't forget the constant. So a real fast use up. Set equal to 2t, crank it out. And the way you can verify it very quickly, what if you take the derivative? If you take the derivative, do you get back to here? If you do, you found the antiderivative, plus c. What about the left, though? On the left-hand side, I might want to take this and just recalibrate it. So it looks a little bit easier to work with. In here, I'm definitely seeing that power rule of integration. So if I integrate, I'm going to take the power, add 1 to it, and then divide by the power, just like that. Okay, solve for y. So I can maybe multiply everything by a negative. And when I do this, again, I'm going to have sine 2t over 2. And this plus c, I want to be a little bit more careful. I don't want to be as clumsy as I was in a calculus class, because it might come back to bite me later in the problem. So I'll just say minus c. Y to the minus 1 over y. And I'm seeing where this is going eventually. I'm going to have to do something with a reciprocal. So it might be to my advantage, looking ahead, to get a common denominator. Take the reciprocal, and you just found the general solution for the given differential equation. So the function which will satisfy this given differential equation must have that internal structure. If it doesn't, it's not a solution. To be a solution, what it means is, if you take this, you plug it in right here, you crank it out, you follow the recipe, that's what this is. You guys realize that? Take a little bit of y prime, take a little bit of y squared, multiply it by cosine, take a little dash and put it all together, put it in the oven, 400 to bake. What pops out? Nothing. Zero. Annihilated. Gone. Okay. So you can always check it by plugging it in and see what you're going to get. That's a little complicated here in this case. So in this case, I probably want to go back and just check my work and make sure it's all valid. The next thing is, I got an initial condition right there. The initial condition is going to lock down the C value. I'm going to know exactly what that C value is. There is an easy way of doing this, and there is a, oh my goodness, this is so complicated, I don't want to do this way of doing this problem. The very complicated way of doing this problem, finding C, is to do it right here. Why is that hard? If I got to solve for C, look at what I have to do. I have to undo everything that I just did. Okay, I don't want to do that. So instead, I'll just back up to where I first see C, do it right there instead. And because I was very careful, very diligent, I didn't say, oh, 2C, I'll just call that C, and over here I'll call that C. I'm not going to confound the variables. I know exactly that this C is the same as this one, and this one when I back up. So then I can very quickly solve. Here, T is going to be 0, so we'll take that, we'll drop that in. And over here, we're going to have -1y, and when T is 0, y is 1. What's the sign of 0? 0. What's C? -1. Come over here and update your equation with the new information you just determined, and there is your particular solution for the given differential equation whenever you have this initial condition. So you can find the general solution. If this is a separable differential equation, what kind of structure must it have? Got to have this structure. So if I cannot factor it, where I have one factor is a function with only x in it, and another one with only y in it, game over. I can't do this process. But if I do, it's game on. I can do this process. So the first thing I observe is there's a y here. I can factor it out. Y prime, you want to take this and just recalibrate. We'll have dy dx. Separate them. X is to one side. And that means the function along with dx. And y is to the other side. And integrate the left, integrate the right. How do I solve for y? E it. Exponentiate it. Okay? And when we do this, we're going to get y equals, we'll have e x squared, e to the third power over 3. And we also have a plus c, but I'm going to break it off and start incorporating this property of exponents multiplied by the same base. Add them. If you add them up, you can definitely break them. The e to the c, I'm just going to recalibrate it, make it look a little bit tidier. I'm just going to simply call it a. And I can't really do anything with a unless I know something about what's going on with x and y. If I was given an initial condition, then I can pinpoint down the particular. Otherwise, I can't pinpoint down the particular. Okay, good. Okay, so again, if I want to solve the differential equation, if I'm going to use this process, I got to ask myself, can I express this multivariable function? That's what it is, right? You have an x, you got a y in it. Can I express it in terms of a product of two single variable functions, an x and a y? Well, one thing we could do is, once again, use properties of exponents. Guys, there it is. So dy dx, separate, x is the one side, y is the other side. You need to bring the dx up. You can't leave it down in the denominator. This, bring it over to the other side, and I'll just say e to the minus 3y. Integrate through. Hit it with a quick u substitution. We're trying to solve for y. Now, again, you're going to run into situations in which you may not always be able to solve for y. If you can solve for y, you get what's called an explicit solution. If you can't solve for y, then you're getting an implied solution, implicit. You got to read between the lines, figure out what y is going to correspond to. So if you run into that situation, okay, don't worry about it. Just leave it in implicit form if you really can't find explicit form. But here, we want to keep pushing along to see if we can multiply both sides and just do a little bit of algebra from here on out. Now, there might be some things you have to kind of really address, because this is possible that maybe this is negative, and if you take the logarithm of a negative number, okay, that's really complex. Seriously, it's a complex analysis. It can really throw things. Can you solve the differential equation? Okay, here's a question. Who's stuck? One person, 2, 3, 4, 5. Okay, so if you're stuck, ask yourself why. Why are you stuck? What are you lacking in this problem that you didn't have or you had in the other problem? Okay, you can't separate it because of what reason? You don't see a what? Okay, so you don't see a function of x. Or do you? Okay, so let me ask you a question. What's a function really? It's, in a simple term, it's not a curve that goes back on itself. So if I was to look at this, that would not be a function. If I had a curve that did that, that wouldn't be a function. Could I have a curve, maybe it's a straight line, would that be a function? Yeah, absolutely. Could I not say that this is this times this? Or am I wrong? That's right. What's this right here? That's a function solely in terms of y. And this, yeah, it's a function, but I could say it's a function in terms of x. Oh, snap. So when I'm factoring, I don't really need to have that x there, do I? Not really. Next thing is separate out dx dy 1 plus y squared. And if you were to integrate across, whenever we're talking about inverse trig functions, I do have to be a little bit cautious about restrictions. I can't just necessarily sweep it under the rug. So I do have to keep that in mind. But what I'm doing here for the time being is just looking at some kind of function that's going to have the right mechanic. And if I want to find y, where this is implicit, I'm not telling you exactly what it is. It's possible that maybe I can turn it into an explicit where I'm telling you flat out what it is. There it is. Now that's pretty cool. One's a factor. Pay real close attention to your differentials when you're going through your problems. A lot of times we do say dy dx. It's just the way we typically do it. We don't have to. We can say dx dy. where I can think of x as a function in terms of y versus y being a function in terms of x. And that's kind of what this says right here. It says how I can interpret that. But again, if it's going to be a separable differential equation, x is to one side, y is to the other side. And based upon if I want to solve for the x or if I want to solve for the y, then I keep going through the process. So here's what you guys need to do. You need to go back and review your integration techniques. It might have been a while. You might be a little rusty at it. There's those videos I dropped for you guys online. Watch those videos, real short videos, about 2-3 minutes, some of them. Just get you back up to speed very quickly. So you got to make sure you're well versed in U substitution, and integration by parts. We're going to do a lot of integration by parts. Partial fractions. Oh yeah, guys, we're going to do a lot of partial fractions here coming up here soon. You might need to do a trig sub. You might need to do something with trigonometric integration. So go back and review those main ideas there of how to do integration. Now, before we leave, I do have this for you guys. These are separable differential equations. And here's the slope field that goes with that differential equation. Look at the first one. That's that dy dx equals 2y, the one that we saw. We know the answer is going to be e to the 2x. Do you see that function going through the flow? Do you see the isocline? Absolutely. When you look at number 2, you're also seeing that exponential. Drop down to number 4, the one that we just worked. Okay. If you were to solve for y, do you see the tangent function going through all those slopes? You can fit it through it. So if it was a go with the flow and not cross corners, because it's a tangent, these are points of tangency on the slopes, slope field, you're just kind of drawing the solution right in between the guardrails. And you're starting to see the connection here, the geometry and the algebra. Wow, look at number 6. That's crazy. I wonder what that equation is. Let's go back to the back page here. Looks like we got a hyperbola, maybe a parabola for number 8, something to consider. 9's like a parabola above, but not so below. Oh my goodness, look at number 10. That's crazy. Wonder what that is. Number 11, kind of crazy too. Now you can think of a lot of different applications. Maybe it's like a magnetic force, maybe some riptides or some kind of current. So you can definitely connect this up with an application very quickly if you wanted to. Okay, so what I want you to do is work through these problems, figure out what y is going to correspond to, get the particular. So find the general solution, find the particular solution, and this is one of y'all's quizzes right here. It's a little take-home quiz. Have this ready to go Monday morning. Other than that, you guys have a great day, stay warm, and I will see you next time.
I hope that today's lesson was a positive and an encouraging learning experience, and that you have a better understanding of how to solve these problems. Be sure to set some time there today and throughout the week to review these concepts, to rework these examples so that you're better prepared for the next lesson. If you need anything, just let me know. You're always welcome to send me an email or to stop by during office hours. Until next time, keep up the good work and have a great day.